Active antennas offer many advantages for high-frequency and millimeter wave applications. They are able to point and steer a highly directional beam in space to overcome challenges of free space path loss, and to maintain a robust signal link to moving objects or changing channel conditions. They are comprised of a row or an array of discrete radiating elements, and by controlling the amplitude and phase of how signals at each of the discrete elements are summed together, the beam can be steered or scanned in space. This technique for controlling the signal phase at each antenna element also results in the antenna sometimes being referred to as a phased array antenna. The ability to change the direction of the beam electronically removes the need for any mechanical scanning requirements, resulting in a smaller and low-profile antenna. The beams can also be steered extremely quickly and also shaped to change the antenna performance. Active antennas have already been used for many years in applications like radar or secure communications. Traditional manufacturing, though, has been using modular components which have resulted in a bulky or large form factor, complex and expensive assembly techniques, and excessive weight and power dissipation. Breakthroughs in semiconductor processing and the high-volume, high-precision assembly techniques pioneered by the likes of commercial and consumer handset industries now means that the same techniques can be applied to active antenna designs and manufacturing, enabling an entire new set of new applications and markets where they can be used. Some of these markets include the traditional application areas like radar, imaging, and satellite communications. They can also add additional flexibility and improve performance to other application areas like satellites on the move, where the increased weight and drag effects of mechanical antennas on aircraft aerodynamics can be replaced by low-profile, electronically scanned antennas. And they enable brand new markets, like millimeter wave communications for cellular and mobile users, where being able to steer a highly directive beam is critical to establishing and maintaining a communications link. All this is made possible by the high integration capabilities of advanced silicon semiconductor engineering. Whereas in the past it was almost impossible to integrate all of the required electronics to steer an electronic beam behind the physically small area or aperture of the active antenna, the high integration available in modern-day silicon processes means that all of the required electronics can be placed close to the antenna as possible. This means that a low-profile planar antenna can be manufactured using standard surface mount assembly techniques, and it also results in the most energy-efficient solution for the link. This is important for reducing the size, weight, and power required to install an active antenna, and also reduces the energy required to power the antenna, an important consideration when energy efficiency demands are increasing with green technologies. Now let's look at an example of an active antenna developed for 28 GHz communications applications under the 5G new radio standards. The active antenna uses the Anokiwave AWMF0108 as a base semiconductor platform in order to enable a 64-element full planar array, as shown in the photograph in the lower left-hand corner. The Anokiwave IC uses a time-domain duplex quad architecture, where each IC directly feeds 4 radiating elements for both transmit and receive functions. This requires a total of 16 ICs arranged in a 4x4 array to support the complete behind-the-aperture electronics required for signal transmission and reception, as well as beamforming and beam steering. Each of the ICs, as depicted in the schematic drawing, contains 4 discrete transmit and receive signal chains that are fed from a single common arm signal for coherent signal combining. Fully independent vector modulation is available in both transmit and receive signal paths to provide full 2D beamforming, with 5-bit precision in both amplitude and phase control. This IC covers the 26.5 to 29.5 GHz frequency range and is controlled over a standard SPI digital control interface. The conducted output power of 9 dBm per element arm can be used to develop significant amounts of EIRP, or radiated power in the far field, as we'll see. The IC is packaged in a standard commercially available 6x6mm QFN surface mount plastic package with full ESD protection on all of the I/O ports, making for a robust and easily handled product. As we saw on the previous slide, combining 16 of the AWMF0108 Anokiwave ICs allows a 64-element full planar active antenna array to be developed. The 0129 is a compact and power-efficient array that, despite its small form factor, allows over 50 dBmi or greater than 100 watts of radiated power to be developed at 28 GHz, while only consuming around 17 watts of DC power. Interface controls are simple and consist of a single 12-volt DC power input, as well as a choice of control port. The array includes an embedded controller that dynamically performs all of the beam steering calculations and can easily steer a beam anywhere within a 60-degree conical scan volume from bore sight by simply entering the 2D vector coordinates on the center frequency of operation. Beam update rates that allow the beam to be steered on a low latency basis are possible. For more information and to see a video with the array in operation, go to the Anokiwave YouTube channel for a demonstration. Anokiwave makes it easier for you to evaluate all of our active antenna ICs with a fully integrated developer kit that includes an IC already mounted on a connectorized evaluation board, a support test kit including all of the evaluation cables and interface circuitry that you'll need, and an easy to install and use GUI to control the software interface, allowing the user to measure, validate and control all of the functions of the powerful IC within minutes. Contact your local Anokiwave sales office or distributor for more details, and happy integration.